So yesterday we were seeing mathematical morphology for binary. Now we will extend these concepts for grayscale images. So let's see how to do that. Okay, so the first, yesterday we saw that one of the key concepts in this mathematical morphology was the concept of inclusion. So we had sets, say that we have these two sets, and then we have to define when the set is included in another set. So this red set is fully included in the B, but A here is not fully included in the B. So this is some intersection, but it is not fully included. Okay, so this is very easy. This is for 2D binary images. But now we have to extend that concept to include the grayscale. So to include the grayscale, we will think of so you have an image and you have some intensity. So the intensity will be the height of of the object that you're dealing with. So the support is here, so it is the same concept as support here. So you have the support, and then you have the intensity. And so for every image, you will have the support of the image and the intensity of the image. And then you will define the inclusion in this way. So for instance, here A is fully included in B because the support of A is included in the support of B, and the intensity of A is all the times smaller than the intensity of B. Here, the support of A is not fully included in the support of B, so this set is not, the red is not included in the blue. What about these ones? This one is not included because the support of A is included in the support of B, but the height of A is not included in the height of B. And here it is the support and height are not included. Okay, so the set now is 3D, and a set is included in another one if the support of A is in the support of B, and the height of A is always smaller than the height of B. Okay? So this is the first extension that we will make. Yeah, so this is just matter of how real numbers work. So if you include minus infinity, that we will use across the lecture, there are some rules like when you add infinity to anything, it's infinity, minus infinity, same. And this is in general, this is a noun. All the limits and this kind of stuff. But for us, here in this context, infinity minus infinity will be same. So this is something special for image philosophy, but it is not mathematically. So mathematically, you have to take the limit. Sometimes it will be zero, sometimes it will be constant, sometimes it will be infinity, but it is undefined. Yeah, so these are the kind of sets that we have created. So they are the collection of points, and these points are made of the location of the pixel and the intensity of the pixel. And these intensities are scalars, so they should not be bold. It should be standard, I, so no more. It is not a vector. And this intensity is in the extended reals. So the extended reals are the ones with infinity. So the real numbers do not include infinity, but the extended real they. Same concepts as we had yesterday. So we have the support of the image. So the support of the image is all those locations where the pixel value is not infinity or minus infinity. We have extended a bit the definition yesterday. And then the background is those locations where it takes values and infinity or minus. Then, so wherever the image is defined, if we have a value, outside there, we will assume that it has value minus infinity. Okay, so let's look at this image. So this image, think of it in 3D this way. So this, you see the intensity defines the height at that pixel. So we have a pixel here, relatively low intensity. We have this low height, and then a little bit brighter, then the height is bigger, and then the next one is brighter, so height is bigger, and bigger. And so this is the 3D representation of this. Okay? And outside these values, it will have the value minus infinity. So outside here, it has our set has value minus infinity. So, for instance, here you have a couple of images, a couple of cones, and these cones, so they have different height, they have different intensity, maximum intensity, and then they decay down to 0, and outside 0, they have minus. Outside here, they have minus. So you have to think of images in this way. Okay. So yeah, so these are the rules that I mentioned before. So when do you say that one of these sets, we are constructing sets of this kind? So when do you say that one of these sets is included in another set? So J is included in I, if the support of J is included in the support of I, and the intensities of J at all the pixels in the support are smaller than the intensities of the image I at the same potential. These are these rules that we're going to discuss in the beginning. Okay, so we had yesterday this idea of having an structured element and shifting it to a location P. So we have to extend this operation now to these 3D sets. So let's say that we have these structured elements. So these are different structured elements. And the translation will be into senses. So the first one is location. So you want to. So we have a structuring element. This structuring element, I've said that it has a number of locations and the intensity value at those locations. They are sets of these pairs. And we have another point. We have a location and the intensity of that location. And what we want is to be the structure element in this location. So this will be a new set. And it will be P plus Q. I say P plus I. And these all points in this report. So it is a set, and we are, so when you do the addition, you're doing the addition in two senses. One is in the location, the other one is in the densities. So let's see that. Okay, so let's say that we have this set, which is the structure element, and we want to shift it to this location. So that will be different location, and there will be a shift in time. So this will be the new set. P plus Q, I Q, because originally it's set was flat. So the height of set was flat. Then we only have I of Q. And this is if we have a flat disk, but we could have any other structuring element. So we could have hemisphere, and then we would have here the hemisphere that is element. Okay, so we have extended the of the structuring element. That I did in the 5 point. And then we have to define also reflection. So reflection, you can imagine, it is similar. So this is said. So said reflective is minus B minus, like I said, B. So B. So this is the way to reflect it. So you reflect the whole thing. You reflect the location and you reflect the intensity. How it is. Try to represent here. So and now we will define the same operations that we did yesterday for binary images, but now for gray images. So we defined yesterday erosion and dilation, and then we also defined opening, closing. So a reminder from yesterday, dilation was making the bright parts of the foreground bigger. So have this original now. The foreground is bigger. Erosion was the opposite, making the background bigger. That this image is darker than this one. We will see how to construct it, but see the background has grown. And then opening was first dilating and then erosion. Closing was the opposite. So we will now define all these operations. And you see they follow more or less the same philosophy as 16. Okay, so let's do it for dilation. So dilation was the one that yesterday was similar to the convolution. We will see that actually this also looks like. So this is the definition of the dilation. So let's see how it goes. So it is, you take all the values in the support of, so we want to evaluate that the point field. So what I have to do is to reflect the kernel and shift it to that location. And when I shift it, there will be a few values that are different from minus infinity that is defined in our support. So the values that are not minus infinity are our support. For all those things, what we do is we take the input image at that location and we add this thing, and we know what this is a point. So this is a point. So is that kind of operations? So we are adding 2 points. The point is something like this. So we have Q I Q as E I B. And this is defined as B I Q. And there is something interesting. These addition is not the same as this addition. Why? This addition, you know that operators are mathematical constructs. So an operator is a function takes point here. This is our definition of point. The definition of a set is a set. And this is producing a set. What about this one? This one is taking a point, another point, and it's producing another. Do you see? Those two signs are not the same. Okay. So here, the one that we are using, the one here, is the one with sets. It's a point. Okay, and then we have another way to compute it. Either we use here set and we add, or we reflect and we solve them. There is nothing we use as and so let us see. And there is another way that is this one. Okay, so let's try to show that one. So what's the convolution again? We want to compute the convolution at the point R. Is just some load of I and now we have I like maybe I said this is the maximum of B. Maybe this should forward and or I pass. So now let's see the structure. The structure, this structure is very typical in. So there is a shift. This sum goes for all the points, the support here. This sum, we don't write it explicitly. Normally we write from minus infinity to infinity, but we know that many of these H are zero. So for all those that are zero, we could also write M in the support of H. We have also written like this, the support. Because otherwise it will be zero, it doesn't matter. And then there is an operation between the shifted image and the kernel. Here the operation is multiplication. Here the operation is addition. It is the same. At least in the sense it is the same structure. And then there is a gathering operator. There is a gathering operator. So here it is summing, here it is computing the maximum. But this one is also like a convolution. As yesterday we also had the binary morphology it has a convolution. And here the image is 15. So we know from the convolution. This is this definition. Now the kernel is small details like have to use here the support of the reflection is that grabbing this one. But the structure is the same. So either you move the image or you move the curve. And then for every point where the operation is different from zero, this is the support the same. So for every point where the operation is different from zero, or different from minus infinity in this case, you make an operation between two, and then you gather all those images from a single one. Okay, so this is formally, let's see how it goes with a couple of images, with one image. Okay, so let's say that we have this image, this is our original image, and we want to dilate it with a flat disk. So this structuring element is a flat disk. So let's say that the disk is very far from the cones. Okay, so let's see the operation that we have to do. So we have to follow this one. That is shifting. This one is shifting the curve. So let's shift the kernel. So what we have to do is to shift the kernel, add it to the point of the image, and then take the maximum inside this set. So set plus point is set. So we put it here, that is very far. This is the location will be here, and the intensity will be minus infinity because the kernel is zero. And the image is minus infinity at that point. Zero minus infinity goes to minus infinity. Okay, so all these results are minus infinity. Okay, so what happens when we get closer to the cone? At some point, we will touch the cone. So when we touch the cone, now we have to compute the maximum of the image plus the kernel. The kernel is zero all the time. Okay, so it will be, all this region will be minus infinity. That's the way. Right. So this is my code, and this is my kernel. So in all this region, it is minus infinity. In this region, I have values that are different from minus infinity. And what I'm calculating is minus infinity in this region. I'm calculating the value at that point. Okay, so it is the maximum of a lot of minus infinities and then some values. So it will be the maximum of these values. So the maximum will be coming from this area, because it is the one that is different from minus infinity. And then that maximum will go to this point. And then you can put your kernel even closer. Then you will have all the time the same effect. This region here is the one that is giving you the maximum. All this region here, yes. All this region here is giving you minus infinity. And what if my kernel is now inside? So my kernel is inside. All this region is giving me correct value for the maximum. Okay, this is our code. And at some point, my kernel will move to a location where it includes the maximum. When it includes the maximum will always be that point, the maximum of the code. See the process? So you're moving the kernel. In all these regions, you're getting minus infinity. At some point, you get values that are different from minus infinity. That's floor one. Subside is one. It's full of minus infinity values. This one is getting values different from minus infinity. Same here, same here. And at some point, you will reach the maximum of it. And then the maximum, the value will all the time be this maximum. So all these regions, they all get the same maximum. So let's see. This is the path we should expect. So it is minus infinity all the time. At some point, we are touching the floor. So we get values different from zero, from minus infinity. And then we get closer and closer and closer to the maximum. And at some point, we are touching the maximum. Then we are getting this plateau here. The plateau is because all these locations, the base is touching the maximum. Okay, so the dilation takes these columns, make them bigger, and they are separated by the maximum value of the image of those in that region. This one is separated here, this one is separated there. Next one. Okay, so let's take an image like this one and let's dilate it. So if we dilate, all the bright areas will become bigger. So all the bright areas become bigger. So for instance, here in the eyes, it's very clear. The eyes disappear because their eyes are dark. Then the nearby bright areas grow and they fill the dark areas. Do you remember yesterday, dilation was filling holes. The eyes are holes from the point of view of this kernel. This kernel is a flat. And this is the result. But for the moment, it is not very useful. And it is like yesterday. So dilation was one of the basic operations. And then we define more complex operations like the one to calculate the boundaries. So this will be one of the basic things. Okay. So this is what this does. Filling holes, making bright areas. Okay, so now erosion. Erosion is kind of equivalent to the binary erosion yesterday. So erosion was making the background bigger or making the foreground smaller. So is denoted by this symbol, and then it is defined in this way. And we see the same structure. So either you see the image of the kernel. So here it is definition here of the kernel. The next one here we are shifting the image. So you shift the here in this definition here the kernel. For every point where it makes sense, you are making an operation between the image and the kernel, and the operation that applies now is subtraction, and then there is a gathering operator. So let's see how it goes. So we are computing now the minimum of the image minus kernel. So let's do it. Let's repeat the same reasoning as we did before. We have operating. This is the code, and we are doing image minus kernel. It's shifting kernel and so, but just to avoid. And we are computing minimum of this. Minimum. Okay, so here the image, so the kernel is 0, so it is a flat disk. Here the image is minus infinity, so we get again minus infinity. This is minus infinity. What about this one? So at some point we touch the silicon, the code. So we get minus infinity here. Get some values there, but we are computing the minimum. So the minimum of this will also be minus infinity. We have some values and minus infinity, so the minimum is minus infinity. What happens if the kernel is fully inside? So now everything gets a value. The minimum will be whatever value. What about if it is including the minimum? So the minimum is not, before we were computing the maximum, and the maximum was determined by the maximum function here. But now the minimum is somewhere else. Minimum is maybe there. Okay, so let's see how it goes. So this was the original. And this is the result. So when we are away from the codes, we get minus 50. When we touch the code, we still get a lot of minus infinities. So this is just the shade of the limit. It has minus infinity values. So all these values are minus infinity. And then at some point, the kernel is fully inside. We are in this situation now. It is fully inside. Now we get real values. Get these values. And when we get to the top, so this value here is determined by the meaning of the disk in that location, not the maximum. In the beginning, then this in that location. The same for you. So at the end, what you're doing is all the gray values, you're pushing them down towards zero. Can go back to here. Now, understand this image. This image is better. You have this original, dilate, make it bigger, the bright part is bigger. Now, if you enroll, you're making this the bright parts smaller. So this representation here as this. This is the same as we were saying also. Either you move the kernel or you move the agent. And this is the result of this reason. So erosion is making that part bigger. So now the eyes should be bigger. They have. And the bright agents should be less bright. They have. So another basic operation. Now let's construct them. So let's put them together. So opening. So opening is erosion, then dilation. First you erosion, and then you dilate. You remember from yesterday that the opening was always contained the original. So here it seems to be the opening is this one. It's with the plateau. Is contained in the original image. And it's contained in the sense that we have defined today. The support of the opening is the support of the original, and the height of the intensity of the erosion of the opening is also related the intensity of protein. Okay, so let's see that these step by step. So we have the original, we the lotion is one, and then you take the lotion, you dilate, then dilate. Here you have the three of them. This opening is erosion and then dilation. And closing is dilating with the reflection and then closing with the reflection. The definition. Closing. So here is the opening. So the opening is, so what is the effect of opening? Effect of opening, see here, is cutting very bright values. We are cutting the very bright values. Let's see this opening here. So this is the image and the cutting of very bright values. Okay, this one is interesting. So first we are eroding. So when we erode, all these black points become together. They become a continuum. And when you dilate them, you cannot recover the original structure. So the original structure is lost. Same for the eyes. The eyes here. So first you erode, then the eyes become a dark area. When you grow, then you dilate them, you cannot recover the original structure. It's not necessarily bad. Depends on what is in purpose. So for instance, let's say that you want to subtract the background. So now you can subtract from this one, you can subtract this one. It will be an effect. We will do it later. So the closing this is the design. Closing was filling gaps in the background. And there was this property that the original is contained in the closing. So here we have the different steps. So we have original, and then you dilate. Once this is the dilation. And now the dilation will hello. Then you get this one. And you have the two steps. So you have the original dilate, and then the dilation you erode again. So closing should be filling gaps. So here we have to fill the gaps. The eyes are gaps. We are filling gaps. Here you see, for instance, now all these black rings here, they are somehow filled. And we have kind of same laws as we had yesterday. So we have the complement of dilation. So the complement of dilation is you have the two sets. This one you have to complement. This one you have to reflect. Complement of erosion. So the first image you have to complement. The second one you have to reflect. And you have also properties for opening and closing. So the complement of closing is opening, the complement of opening is closing. Here we have same operation, same experiment as we did yesterday. Let's say that we have this original image. Now if this is not binary, it is Grayscale. Then we do dilation with this L that has 0 value in height. Then this is the dilation. Dilation, always think of dilation as a kind of, it's a non-linear. So we should see that, for instance, this in this direction, it behaves as a delta. more or less. So we should see kind of delta or the head all the time. That's why we have this structure. The other ones, they don't behave as they have the same structure as the evolution, but they don't. The result doesn't look like a convolution. But it is a non-linear. Actually, this is interesting. Where is the non-linearity come from? When you see this expression, so this operation is linear, this operation is not linear. So where is the non-linearity coming from? The maximum. The maximum is a non-linear operation. So, and the addition is linear. Okay, so this is dilation, erosion, opening, closing. So, erosion is background becomes bigger. This is the background becomes bigger. It becomes bigger with the shape of the tangent. This picture. And here the background also becomes bigger. And opening is erosion followed by dilation. Because cutting peak of this peak is removed. And closing is filling gaps. So this gap, which is down here, is filling. And this is dilation of reflection. Any questions? Okay, so let's define more advanced operations. So the first one will be this top hat. Okay, so the top hat is defined as the original minus one. So we were saying opening is cutting the very bright point. This was the original, everything was the original, and then the top hat happens. The opening was this one that is somehow shadowed. So what is left? Is left what has been missed. Has been missed is peaks of the cones. So this top part is original minus original. So just the peaks. So when you compute the opening, you are cutting some regions. So the top part is what you have cut. Okay, this is what we have cut. And now, so it is original minus opening. So opening was the very bright points were removed. So these are the bright points. Bright points are right here, this one. So now we have a point detector, bright point detector. Now these images, they have more. So they are not so true. Statements. So we will say closing and opening, they are not very useful. A lot of information. But the opening and closing by themselves, they are just reuse to construct more sophisticated operations. These sophisticated operations, one of them is this top hat. Now this top hat takes the bright points. Here it says it has been shown as negative of the visibilities. The black points here are the bright points of this one. So the bright points are this one, so very bright one here. They appears this in so it is a bright point detector. What about the bot hat? Bot hat is the option. Here's the issue. So it is closing minus original. So we have the closing original and the closing underneath. The closing was within the gap. And this closing minus original. So that means what have you filled? So closing is filling the gaps. What have you used with the gaps? This is the point. Fill the gap with this amount. So now it is a dark area detector. Dark area detector. All these dark points should appear this dark area detector. The eyes will also appear. This filling the gaps, so filling the dark areas. Now we have a dark area detector. Very dark area. Here we have the two top hat and top hat. Top hat is bright point. Top hat there, dark point. And now we can subtract the two. Top hat minus top hat. And this should be a kind of edge detector. So now we have an edge detector that is non-linear. So we have seen linear edge detectors that are the ones that involved with, you remember these kind of detectors. We have these barriers here. One, and this was an edge detector in this direction. Now we have a non-linear edge detector, and the structuring element is a this, so it is a non-linear edge detector in all directions. But if you want to have an edge detector in this direction, the structuring element should be aligned. By deciding the structuring element, you can detect edges in whichever direction you want. Question here. So, point to make a break. Okay, so we will use these grayscale morphology to make another grayscale reconstruction as we did yesterday with the binary reconstruction. You may remember from yesterday, binary reconstruction was the one that was removing the noise. So the process is the same. So we start with an opening, and then we will do something until the image doesn't change. And this thing that we will do is dilate some element and then computing the minimum between the input image and J. So J will iterate, and at every point, at every iteration, we will compute the minimum between I and J pixel-wise. And we do that until the image doesn't change. Okay, so let's see how it works. So let's say that we start with this opening, and then have the opening and the original. And this is the reconstructed image. So you dilate, and then you compute the minimum between dilation and input image. And then you dilate again. So you see that it can recover a bit of what we cut. So the opening is cutting quite a lot of the bright points, and this grayscale reconstruction is recovering a bit. It doesn't fully recover it, but only you may remember from yesterday it had a lot of noise, so you don't want to take over the noise. The noise. So fully get into the input image, probably it's not a good idea. So here you have some example. So let's say that this is original, this is the opening. The opening has removed all the bright points across has disappeared. Now the reconstructed, but that it has also changed the shape. This was kind of cross or square. Now it became something more round. Now the reconstruction has recovered a bit of the original shape. Then you can look at the differences. The difference is this original minus opening because all this cross and the top of the is very big. And then original minus reconstruction. This is now the only part that we are missing for this the part of the cross you have recovered, and then this is the difference. This is what you have recovered. Size for the cross. And here you have, for instance, the original, the reconstructed opening. So the reconstructed opening is somehow removing the very bright parts. So you see this bright region here, this bright point has disappeared in reconstructed. But otherwise, the rest of the image looks more or less very bright points have disappeared. And we know by the tools that we have used that this is done in a non-linear way. These are the different steps. This is opening, this is beginner, this was reconstructed. So, yeah.
You said that Rosie fills the dark and as a dark area of the center.
Not the crossing, but the box hat. The box hat is a dark area.
La theta acá.
La Z es el que lo hemos llamado elemento estructurante. Lo llamáis kernel tampoco. Como el nombre técnico es elemento estructurante.
Se rellena todo el.
El closing, sí. El closing era el que hace. Ya hay. Y las dos montañitas rellenan. Y el box es con que has rellenado. Se rellena con este trozo.